Good day, I'm Norman Walberger. Today we're going to carry on with this new framework for linear algebra and matrix algebra. So we've been talking about pixels and maxels. A pixel is something like this. It's a list of two natural numbers. And a maxel is something like this. It's a multiset of pixels. And last time we introduced the multiplication of pixels. That KL times MN is the pixel KN, provided that L equals M, and is otherwise empty or blank. And then we saw that this naturally extends to a multiplication of maxels, that we can then take this pixel multiplication and create a multiplication of maxels out of it. So for example, this maxel here consisting of these three pixels times this maxel consisting of these two pixels is this maxel with these three pixels. And the way we get that is we take each of these pixels in this first multiset and multiply them with each of the pixels in the second set, all possible combinations, and put all of those combinations together in a multiset. So 1, 1 times 1, 3 is 1, 3. 1, 1 times 2, 7 is the empty object, so it doesn't appear at all. It doesn't make any contribution. Then 1, 1 times 1, 3 gives us another 1, 3. We have to put every element in with the correct multiplicity here. 1, 1 times 2, 7 again gives us nothing. 4, 2 times this gives us nothing, and 4, 2 times 2, 7 gives us 4, 7. So we get then a very interesting and rich structure. This realm of maxels that we talked about last time with the operations of addition, union, and intersection is now augmented with this new operation of multiplication, which gives it a very rich structure which has huge amounts of implications and applications to mathematics. So in today's video we want to establish some additional aspects and notation centered around this multiplication of maxels. So our first theorem is the distributive law, which tells us that for maxels m, n, and o, that m times n plus o equals mn plus mo, and m plus n times o equals mo plus no. So this is actually a general consequence of the fact that our multiplication of maxels is a multiset analog of a multiplication at the fundamental level of the objects. So for example, suppose that M was a multiset with elements A, B, N was multiset with elements C, D, and O was a multiset with element E. And we could be rather general. These could be pixels in a maxel, or they could be other kinds of objects in some other kind of multiset. Now, when we add these two M sets, we know that what happens is that they just form a bigger M set, combining all of the elements with the appropriate multiplicities. So we get C, D, E. And then the product of these two M sets is, well, in terms of the multiplication of the individual objects, AC together with AD, AE, BC, BD, BE. All possible products of these guys with these guys. And now if we look at this, well, we can rearrange it a little bit. AC, AD, BC, BD, and then moving the AE over here, BE. And that way we can separate this into, the first four is AB times CD, because that's AC, AD, BC, and BD there. And then the last two is the same as AB times E, because there's an AE and a BE. So this illustrates that it's a very general consequence of the fact that we're working with multisets here. So the vector space structure of the multisets is kind of given to us automatically, and if we have a multiplication of the objects in the M sets, then we automatically have a distributive law in this nature. Okay, so along very similar lines to the previous one, we have an associative law that for maxels mn and o, we have mn times o equals m times no. This is a very important law. Okay. It's the analog in this maxel situation of the associative law of multiplication for matrices. And that's a rather subtle business. Here in this situation, we can see it as a very general consequence of the fact that our multiplication of pixels, upon which our mset multiplication rests, is itself associative. So there's a general consequence of having an mset multiplication defined by an associative multiplication of its elements. So let me again give you an illustration of the argument without sort of laying out the whole thing in gory detail. So I hope this captures the reason why this works in great generality. So it doesn't really depend on the particular nature of our pixel multiplication. It only depends on the fact that we know that it's associative. Okay, so for example, here's one mset M, which is AB, another mset N, which is CD, and O is this one here. If we multiply these two, we get the mset AC, AD, BC, BD, all possible products here. And when we multiply by the mset E there, we get all possible products between these guys and this one. So we get AC times E, AD times E, BC times E, and BD times E. Okay, now the crucial step is to go from here to here, which is to use the fact that we're assuming that the underlying multiplication of these objects, whatever they are, is itself associative. So that this AC times E can be rewritten as A times CE. And similarly for these other ones, they can all be written in alternate fashion, exactly like that. And when we write it like this, then we see that we can rewrite that as AB times CE/DE, because here's A times CE, and here's A times DE, and then B times CE over here, and then B times DE over here. And then once we've done that, we recognize that this is, well, there's the first one, which was M, and then CE times DE is just the product of these two. So this illustrates the argument in a particular case, but if we made these msets bigger by adding more elements, nothing essentially changes. It's exactly the same argument. Okay, and it's independent of the particular nature of the multiplication. Just what's required is that it's an associative multiplication at the level of the objects. Now we're going to exploit the fact that we're working with multisets in another way, by identifying some very important maxels which are particularly simple and small. We're going to call these one maxels. So what is that? Well, a maxel with just one pixel as a single element, in other words with multiplicity 1, is going to be called a one maxel. So for example, this thing here is a one maxel. There's a single pixel mn inside it, and it's an mset consisting of that single pixel mn. And we're going to give this kind of maxel a particular name, notation. We're going to call it E, M, N. So EMN is just the maxel consisting of the single pixel MN. So for example, E1112 is this maxel, E14.2 is that maxel, E34 is that one, and E11 is that one. Now, every non-empty maxel is a linear combination of one maxels. So here is a maxel, 3, 5, 1, 1, 3, 2, 14, 8, 1, 1, 1, 1, 3, 2. Remember, when we have a multiset, we can use our linear structure that multisets naturally come with. We can rewrite this as 3 times the multiset consisting of 1, 1, because the 1, 1 appears 3 times. Plus 2 times the multiset consisting of 3, 2, because 3, 2 appears twice. And the multiset consisting of just 3, 5, and the multiset consisting of just 14, 8. So we then can use these sort of singleton maxels as building blocks to build up more general maxels via linear combinations. So very similar to the kinds of things that we were doing when we were talking about multisets of natural numbers. except here we have some sort of particular notation that makes it a little bit easier for us to write that down, so we don't have to write lots of brackets inside other brackets. And this will also be more in line with a kind of a matrix point of view. So from a matrix point of view, something like E32 would represent a matrix which is mostly all zeros and just has a single 1 at the 3-2 position. But it's really a bit more than that, because it's not a matrix of a particular size. This Maxel doesn't have a specified size. It just lives in the world of Maxel land, like it's an occupant of the screen, and the screen extends beyond our view. So it's a little bit different, but it's definitely analogous to sort of familiar matrix kind of notation. This proposition gives us an alternate way of writing down our basic multiplication of pixels at the level of 1 maxels. So we've talked about what a 1 maxel is. These are very simple, basic kinds of maxels with just 1 pixel. And now the product of two such things is going to be given by essentially the same rule as the rule for the underlying pixels which it contains. So EKL times EMN is going to be EKN if L equals M. And otherwise it's going to be what we're denoting by capital O, which is the empty or zero maxel. So when we multiplied pixels, if we multiply the pixel KL with the pixel MN, then if L does not equal M, we saw that we got just emptiness there. But here we're talking about multisets containing those pixels. So when we take the product, in that case, we would get a multiset with an emptiness inside it. Well, that actually is a legitimate object and a familiar object in our world. It's our empty Maxel. So this form of the sort of pixel multiplication might be more comfortable for you in the sense that now there really is something that's occupying this position. It's not just a blank, which was rather a novelty for us, wasn't it, in the last video. So for example, otherwise it's very familiar. So E13 times E34 equals 14. The 3 that's there are common, right, so that we're getting something that's non-empty, and what we're getting is just the outside ones. E21 times E31, here the inner ones are not equal, so we're getting the empty Maxel. E34 times E13, also the empty Maxel. And note in particular that Maxel multiplication is generally not commutative. For example, E13 times E34 is not equal to E34 E13. So that's an obvious but important thing to note, that our Maxel multiplication is not in general commutative. And then, well, we can do multiplication at the level of these linear combinations. So we don't always have to write out now our Maxels with all these brackets. We can write things in this form. So this is another way of writing a Maxel. 3e times e11 plus 5e12 plus e42 multiplied by e17 plus e23. Okay. So we can do the multiplication now just using the same rule. So this times this, that'll be 3e17. This times this doesn't give us anything. This times this will be 5e1. No, this times this doesn't give us anything, but this times this gives us 5e13. This times this doesn't give us anything. This times this gives us e43. Now let's move closer to connecting Maxel arithmetic with matrix arithmetic by showing you how to display Maxels on our screen. So remember that in this subject we're using the word screen rather in a precise way. We're talking about this framework here of positions on a two-dimensional diagram, starting with 1, 1 here in the top corner, and then 1, 2, 1, 3, and so on, and then 2, 1, 2, 2, 2, 3, and so on. So this is going to be the screen. Notice also that I've underlined in red the diagonal elements. They are particularly important in the theory and will often be useful for us to keep in mind where the diagonal elements are. Right, so what we want to do now is we want to take a maxel, like this one here, 1, 1, 1, 1, 3, 3, 1, 4, 2, 1, 3, 2, 3, 2, 3, 2, which can also be written in our sort of multiplicity form in terms of these E11s, these 1 maxels. There's 2 1, 1, so that's 2 times E11 plus E21, that's that one, plus E14, that's that one, plus 3E32. 1, 2, 3. What about E33? Better include that one as well. Plus E33. Okay, and so now we're going to display that. I can see that we're going to have to augment our display. What we're going to do is we're going to record the various multiplicities of our 1 maxels on the screen. So this 2, which is in the 1, 1 spot, tells us that our maxel has 2 1, 1s. There are no 1, 2s, there are no 1, 3s, there is a 1, 4, there it is there. There is a 2, 1, yes, no 2, 2s, no 2, 3s, no 2, 4s, etc. There's no 3, 1, there's a 3, 2, in fact there's 3 of them. So there's a multiplicity there of 3. And there's also that E33 that I need to add. So we'll put it there as well. Now we could also say, well, there's also 0, 3, 4. So we could add a 0 there. In fact, we could add a lot more zeros. We could then say, well, there's also 0, 4, 1s and 0, 4, 2s and so on. So this display of M is not entirely unique in the sense that we can always add more zeros below or to the right of whatever we have. Nevertheless, this is getting pretty close to a matrix kind of object that is encoding our maxel and sort of connecting things with a two-dimensional table of numbers. So when we're representing maxels on the screen, it will be important for us to have some notation, an understanding of regions of the screen. So we want to talk about regions of the screen in terms of sets of pixels. So there's a bit of an interplay here between multisets of pixels and sets of pixels. So again, we see the advantage in having rather clear distinction in our minds between these various types of data structures and when it's appropriate to use one kind and when it's appropriate to use some other kind. And being flexible, but still having these various possibilities at hand. Very important. Okay, so we have seen already that in general, if we have a set like A, the set 4, 7, 1, that we can associate to that an M set. A, say, sub M equals 4, 7, 1, just by replacing the braces with square brackets. Okay. Now we'll observe that there's also a way of going from an M set to a set, which is very, very natural. That we can associate to an M set M, and let's just say an M set of natural numbers. This is actually an M set from 5. The M set 3, 3, 4, 4, 5, 1, 5. We can associate to that the set S, 3, 4, 5, 1, which contains the elements of M, but exactly only once. That is where we've removed all multiplicities, reduced all the multiplicities down to just 1. So instead of having 2 3s, now we only have 1 3. 2 4s, there's only 1 4. 2 5s, there's only 1 5. 1 1. And we're going to give that a name. We're going to say that this set S, obtained from the M set M, is the support of M. And we'll use this notation, SUPP, standing for support. So support of M equals S. So that's a very general kind of thing that we can do whenever we have M sets of any kind. We can always reduce the multiplicities down to 1 or 0 then, and then we get a set, and so we can change our brackets into braces accordingly so that we register the fact that we have a set. Okay, now let's go back to the framework of maxels and pixels. We're going to introduce this idea that a set of pixels is now called a frame. We've talked about an mset of pixels, we call that a maxel. So if we just have a set of pixels, we're going to call that a frame. And that terminology has sort of been chosen so that it fits in with our sort of screen view of what's going on here. So if M is a maxel, then the support of M will be denoted F of M, or sup of M. So the maxel M is by definition a multiset of pixels. So its support will be a set of pixels. A set of pixels is what we're calling a frame. So it makes sense to say that this is the frame of M. So given a maxel M, its support is F of M, the frame of M. So let's have a look at an example. Here is a maxel M, 2, 1, 2, 1, 2, 2, 3, 1, 3, 3, 3, 3. What is its support? Its support is what we get when we form a set where all of these elements here are just replaced with a single fellow. So 2, 1, it's a single 2, 1, 2, 2, there it is, 3, 1, and the 2, 3, 3 is replaced with a single 3, 3. Now here is a display of M. We've agreed that we can represent this maxel with this sort of list of multiplicities, but it's a kind of a two-dimensional list because this is a two-dimensional situation. So we have 2 2 1s, we have a single 2 2, we have a single 3 1, we have a pair of 3 3s. So this is a display of M. And now over here to the same screen, but now I'm just showing you the regions of the screen. Over here is a picture of the frame of M. Right? That's just the underlying set of pixels that are represented by non-zero multiplicities over here. So here, 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 and here we have non-zero multiplicities. So the corresponding frame is this set of pixels. It's this one up here, but we can visualize that set in terms of this region. So just by drawing a region on the screen, we exhibit this frame. So we can visualize the frame F of M as a shaded region in the empty screen. A maxel and its frame. So regions in the screen, or these frames, will become important for us. There will be an intimate connection between the algebra of matrices, or the algebra of these maxels, and the geometry of regions in the screen, as we'll see. And if you do a lot of matrix calculations, becoming familiar with this geometry is quite important. So to have a few definitions about the kinds of frames that are appearing is useful. So here are some important kinds of frames that figure naturally. So this kind of frame, which is just a rectangle in the screen. So here's a rectangle, 2 this way, 3 that way. We'll call that a box frame, or maybe rectangle frame, but box is simpler. Okay, so that's a box frame. And let's refer to the special case where that box is adjusted so that aligns with the top and the left-hand side. So it actually is touching that corner. We'll call that a corner box frame, let's say. Okay. These kinds of frames are particularly important for us because they're naturally going to be the frameworks for matrices. Right? A matrix is just going to be a sort of filling of a particular frame corresponding to a maxel. But occasionally we'll have use for other kinds of frames, maybe a little bit more sophisticated. So for example, a somewhat more advanced topic, this is a tableau frame. It's like a corner box frame, but there's a union of them. So it's by definition a union of corner box frames. So it's something that sort of wanders around like this. You can see there's one corner box there, and one there, and one there. Together they form this frame which we could call a tableau or tableau frame. And then another frame that will be useful for us, rather more specialized one, is a frame just with 4 elements, where we've picked 2 rows and we've picked 2 columns, and those 2 rows and 2 columns determine 4 pixels. So that set of 4 pixels is a 4 frame. And we'll see also that that's a useful notion. Great, so we've got some familiarity now with the basic algebra of Maxells and some of the connections with the geometry of the screen. We want to go a little bit further now and develop some more intuition as to how the multiplication really works. This is actually very useful hands-on kind of technology that's important when you're doing linear algebra. When you're doing linear algebra, you end up multiplying matrices a lot. And to have a good feeling for how matrices multiply is really what we're after here. Except we're kind of having a bigger view of that whole story with this Maxel arithmetic. So that's what we're going to do next time, is develop our geometrical feeling for how multiplication of Maxells looks like in our screen frame orientation. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.